Friends, we are back, and this time we are going to discuss about controller tuning. Tuning means what should be the value of Kc, what should be the value of tau I, what should be the value of tau d. By now, you know what's the meaning of all these three terms, and this tuning can be done in two different ways. We shall first be discussing the one which was developed by Cohen and Kuhn. These were the two chemical engineers who were into the process control, and they actually followed the quarter decay method. They actually applied ISE techniques, and they came up with some results which are very easy for us to apply as such without going in for much botherations and mathematical calculations and so on and so forth. Their technique is known as process reaction curve method. So why it is called process reaction curve method? Because as you can see, this entire feedback loop is not a closed loop, but it is opened from this point. It is disconnected from this point. It is no longer a feedback control. It is an opened control loop, and in this open control loop, we give a step change. And mind you, you very carefully observe the step change is not a unit step change, but it is a step change of the magnitude capital A. So this is what is given to the final control element, which acts upon the process, and it brings about a change which is monitored. This Y is monitored. Now since there is no feedback, so this change in Y is not going to affect anything directly, but whatsoever is the change, whatsoever is the step input of magnitude A is given to the flow to the final control element. It may be a valve, it may be changing the flow of some fluid to the process, etc. And the output, whatsoever it is, it's a pressure or density or composition or temperature or whatsoever, that is recorded over a period of time. So that is taken as the process reaction curve method. So this curve is plotted, and from that curve we shall be seeing some of the parameters. So those parameters we will be deciding, recording, and those recorded parameters will be used to tune the PI, D, PI or P or PID, whatsoever kind of controller you want. Those parameters will determine the values of Kc in case of P alone, the value of Kc and tau I in case of Pi, and the value of Kc, tau I and tau d in case of PID controller, which will be ultimately used in this loop. But before that, before it is properly tuned, this loop is opened. And since this loop is opened, this becomes one of the limitations of Cohen and Kuhn method, that for some period of time this loop needs to be opened. In some of the very critical kind of applications, you cannot afford to open the loop because you have to control it manually. In case this controlled loop, it goes awry, it goes out of control, it can be a very dangerous or a tricky situation as such. So in spite of the fact that this Cohen and Kuhn method has this limitation of this process loop being opened, and how this limitation is overcome by another control loop, we will see. Let us first of all understand how this Cohen and Kuhn method actually works. So once we have given a step change of the value A, let us say the process, mostly the processes, they behave like this. They follow this sigmoidal curve, and they reach a new steady state value, and that steady state value has the final value of B. You remember, input was A and the output, the final output is B. So what should be the gain? The gain becomes B upon A. This is what is given over here. So here we find, first of all, we find the point of inflection. The point of inflection. This is the point of inflection. How do you find point of inflection? Because you see, this curve is concave. This curve is concave, and this curve is convex. You can all see this curve is convex. So this is the point. This is the point where the concave curve becomes convex. So this point is called the point of inflection. This is called point of inflection. So what we do is we draw a tangent at this point. Whatsoever is tangent to this curve, that is drawn at this point, and the slope of that tangent is taken as s. Slope of that tangent becomes s. So this s is one parameter which we have seen from the curve, and wherever this slope, wherever this tangent, it intersects the x-axis, so that point, that interval is called td. That interval is taken as td. So ultimately what we see is that we are going to approximate this entire curve, as this curve is made up of, first of all, dead time. This is the dead time element, followed by a first order curve, and the first order curve is approximated, its approximated response. This is the first order curve, and we have the slope s over here. So what do we see is that we will find the time constant, we will find the time constant tau of this. And how is that found? It's very simple. If you can see, if you see, if you just can imagine that this is one triangle, I drop a perpendicular from here, and then if I draw a perpendicular from here, then you see that this point from here to here, this time constant is tau, and that tau is given over here. So how to find tau? If this is the height b and this is tau, then b upon tau is equal to slope. Then b upon tau is equal to slope. Or conversely, you can find the value of tau from this slope which is known, and from value which is known. So that tau is used here, this td is used here. So this entire open process response is jotted as, is approximated as the first order delay, some pure delay followed by first order system with time constant tau and with gain k. So what will be gain k? Gain k will be equal to b upon a, and tau, this tau is determined as from the slope. This is capital slope s. Do not confuse this s with this s. This s is for the Laplace transform. This is a small s, and this is the slope capital S. So do not confuse, these two are not interchangeable. So this s is equal to b upon tau. This s is equal to b upon tau. Therefore you can always calculate tau as b upon s, just the converts. So this is what we are going to see in the next slide. So once again, as stated, the gain k is given by b upon a. You all know b is the new steady state value, a is the input, the magnitude of the step input which was given to that, and this tau is determined from b upon s. This is what I've been telling you again and again, where s is the slope of the sigmoidal curve at the point of inflection. You also know what is the meaning of point of inflection. And tau d, where this tangent drawn at the point of inflection, it cuts the time axis. At that point we take that as the approximated dead time tau. This td, that is the time elapsed until the system responded in its approximated curve. So friends, as I said that this pair of chemical engineers working on the process control, they applied one quarter decay method. They wanted to have a minimum offset in case of P controller, for examples, or a minimum integral square error, because you see that in case of proportional controller, the offset is never ever equal to 0, so you cannot apply integral square error. So in case of P, you will be going in for a minimum offset kind of technique, whereas in case of PI and PID, you can apply ISE. We have applied ISE, and then they came up using this criteria. They came up with something which is very eye catching and simple to use, as we shall be seeing in the next slide. So friends, what did they actually propose? That in case you want to go in for proportional controllers, you know the value of k, you know the value of tau, you know the value of td. This is what you have so far computed. Then simply use this formula. No need to go in for something very tedious kind of things in calculating ISE, modeling, shortening, nothing to be done. And what we will be doing is simply put in the value of Kc as equal to, given by this expression, 1 upon k, tau upon td, into bracket 1 plus td upon 3 tau. Now, the interesting part is that in case you don't want to go in for proportional controllers, you want to go in for proportional integral controllers, what we call it as PI controllers. In that case, instead of using this Kc, you use this Kc. Why? Because we know that as you add the integral term, the order of the system, it increases, the system becomes sluggish, the system starts giving more deviations, the maximum deviation increases, and the system starts oscillating. So this oscillatory system can become unstable and lead to the instability. Therefore, the value of Kc needs to be decreased. That is why you see instead of 1, you have zero point 0.9. It means the value of Kc has decreased in this case. Similarly, not only you have 1 up Td upon 3, instead of you have Td upon 12, this further decreases the value of Kc. This is the point which we have noted over here. Why has it come? Because we have now gone in for proportional integral controller, and for the integral value, the value of the integral gain, which is actually Kc upon tau I, it is upon tau I, it's the time per repeats. So that value of I is given by, this is the term 30, this is term 3, and so on and so forth. This is the value of tau I. Now, in case you want to go in for PID, the moment you go in for the value of tau d, the moment you go in for the value of tau d, then what do you see? First of all, the value of tau d is given by, again, this expression. You know the value of td and you know the value of this. This has a damping effect, and the good thing about damping effect is that the gain of proportional can be increased as compared to the normal p. You see this gain is more. Here you had 1, and in this case you have to reduce it. In this case you can actually increase it by adding 4 by 3. Here you can see is 1, here it is 0.9, here it is actually 4 by 3. It means that the gain can be increased, the system responses become quicker, and even the value of time per repeat, that time has also gone, it has changed. You see, from 30 it has become 32, it has gone higher, from 3 it has become 36. It means that you can go in for even lesser integral, you can have lesser integral leading to more stability, right? So you, this is what you have to keep in mind always, the relative terms as they are over here. So once again, as compared to p, when you go in for pi, the value of Kc goes down because I tends to make the system more oscillatory, so we have to go in for lesser gain. But the moment you go in for the derivative control, the addition of derivative control, the contribution of derivative control is that this gain can even further be increased. So using these values, depending upon whatsoever you want P or PI or PID. So instead of going in for full mathematics and going in for the process modeling and so on and so forth, we simply make use of these things to get a fairly good response, which can further be fine-tuned later if at all you feel like. But this is giving us a good starting response. This is the crux of Cohen and Kuhn method, which of course it suffers from one major limitation, that to know the process reaction curve, every time you want to retune, every time you have to open the loop, and that is something which we normally don't want in many cases. So we go in for another process which makes use of the data not from the open loop response but from the closed loop response. So unlike open loop response, we are now using the closed loop procedure, and this method was again given by Ziegler and Nichols, or some people call it Nichols, whatsoever you want to pronounce it. So Ziegler's and Nichols, these two gentlemen, they gave this technique which covers the limitation of Cohen and Kuhn open loop method. So how does this go in for? It's very simple. You follow three steps. In the first step, what you do is you don't open the loop. You bring the entire process at the set point, stabilize it, somehow stabilize it manually, automatically, hit and trial, whatsoever manner, stabilize it. And then what you do is you give small change, small disturbance anywhere, and then you go on increasing the gain. As you go on increasing the gain, the system starts oscillating, and as the system starts oscillating, the system will oscillate and then it will decay down, and system will oscillate and decay down every time you give a slight up change in the set point, a slight down change in the set point. You go on increasing the gain, but ultimately when the gain becomes so large that the system does not want to come back to decayed oscillations, but rather it results in sustained oscillations. Let us say you have made gain is equal to 1. There was some oscillation, but that oscillation was decaying down. You make it 5, it's still decaying down. You make it 10, it's still decaying down. But at, let us say, the gain equal to 12 or 12.5, the oscillations are sustained. They are not decaying down. They are continuously oscillating and oscillating and oscillating, and they are oscillating with period P. They're oscillating with period P or PU, whatsoever you want to call it. So you record the gain at which the oscillations become continuous, and you record the period of that sustained oscillations. So that is what we are going to see, those two things, the gain and the period of oscillations, these only two parameters, because in previous sections we see we had to have tau, and then we had to have td, and then you have to have k. There were three parameters which were used in case of Cohen-Kuhn method, but in case of Ziegler's and Nichols method, you use only two parameters, k and p. You can call it ku or pu, whatsoever you feel like. So this is what is summarized in this text form over here, that you first bring the system to the desired operational level, and you use only proportional controller, you use only gain and nothing else, and you don't open the loop, you keep the entire feedback loop closed, and you keep on increasing, you keep on changing the proportional gain till the system starts oscillating continuously. And once it starts to oscillate continuously at that gain where it starts oscillating, we call that gain as k or ku, and we note the period of oscillations, and that period is called P. We will make use of this K, we will make use of this P ultimately to know the correct values of PID. This KU is ultimate gain, and this PU is the ultimate period of sustained cycling, and that KU and PU will be used as it was done earlier. Again, a table is given in the next slide for the optimal values of P, I, and D in all the three cases, whether you're using only P, or you're using PI, or you're using P, I, and D. Friends, once again, what do you see over here? The same thing. You have a gain. In case whatsoever is the ultimate gain may be 12, and you want to use it for proportional, you just divide that by 2, and the moment you divide that by 2, you will get 6. 6 will be the gain. That is the gain over here. And in case you don't want P, you want integral to be there, the moment you introduce integral over here, and again you see that this integral means you have to find the value of tau I. The value of tau I is to be given by pu divided by 1.2. This is what Ziegler and Nichols they proposed. And introduction of I tends to make the system more oscillatory, less stable. So that case, you have to slightly decrease the gain. You can see that this gain is decreased from divided by 2, it is 2.2. And again, the moment you go in for the value of D is introduced, the effect of this D is to stabilize the things, to dampen the things, and therefore dampening of this entire system results in we can afford to have higher values of the gain. We can afford to have higher values of gain. That is why as compared to this, or even as compared to this, as you can see, it is divided by 1.7. So this gain is highest in case of PID controller because this is the effect of damping over here. The trend is the same, the philosophy is the same, the concept is the same, but it has two advantages. Number one, we have only two parameters, Kc and tau I, and another bigger advantage is that you don't have to open the loop to know the process reaction curve as such. So this is to conclude the entire thing, that the introduction of I, we have to reduce the gain, but introduction of D, this gain can be increased. So my dear friends, this is, I think you can actually practically do it in the labs, on the simulators and Simulink and so on and so forth. As the time comes, we shall be doing it in the practical labs also. But this Ziegler-Nichols method and Cohen-Kuhn, as whatsoever may be applied, this is a very good starting point to know the tuning of the PID controller, which can further be refined by many methods, but it's a good starting point as such. I've been telling you again and again to get the values of the gains of proportional, integral, and derivative control. So this is all about controllers and tunings. We will further go to something like what are the actuators and how do we physically realize the values of the controllers in analog domain, in P or in PI or in PID, using op amps or using pneumatic nozzle flapper units and so on and so forth. We'll be using number of actuators, the hydraulic actuators, the stepper motors, and so on and so forth in the remaining sessions. Whatsoever are left, we are nearly over with this syllabus, other than the actuator part that we shall be doing in the subsequent sessions as such. So it's over for now, and I am grateful that you have gone through all these things. I hope you have gone through all these things in the same sequence with a good amount of zeal and patience. In case you have any queries, you can always contact me through all the methods available, through Zoom or through WhatsApp or through phones or through learning management system or face-to-face contact, as the case may be. I once again thank you for being with me. I wish you a very safe stay. Enjoy learning. Bye bye. So once again, as stated, the gain K